All right, welcome to The Explainer. Today, we're not just telling a story, we're opening a case file on reality itself. We're going to be chasing down the clues from Pauline Gagnon's fantastic book, Who Cares About Particle Physics, to really try and understand the very fabric of our universe.
So let's kick things off with the first piece of evidence, and honestly, this one's a shocker. Everything we can see, every single star, every planet, you, me, everything, that's only 5% of the known universe. Just 5. That means a whopping 95% of reality is made of these two mysterious things we call dark matter and dark energy.
You know, this is genuinely one of the biggest mysteries of all time, and it's basically turned physicists into cosmic detectives. So let's do what they do. Let's follow the evidence.
Now, every good investigation has to start with what you already know, right? And in the case of the universe, our first set of clues lies in the fundamental nature of the matter and energy that we can actually see.
To make any sense of that little 5%, physicists have this incredible book of clues. It's called the Standard Model, and it's our absolute best description of the subatomic world.
So here it is, our cast of characters. And here's the wild part. All the ordinary matter that you have ever seen or touched, your body, your desk, the air you're breathing, is built from just that first column. Just up quarks, down quarks, and electrons. That's it. That's the recipe for everything tangible.
Okay, so you can basically split all these particles into two families. You've got fermions, which are the building blocks of matter, and bosons, which carry the forces. Now, fermions are, they're kind of standoffish. Because of something called the Pauli exclusion principle, two of them can't be in the same state at the same time. And that simple rule is why matter is solid. It's the reason you don't just fall through your chair. Bosons, on the other hand, they're social butterflies. They love to group together.
So how do forces actually work at this incredibly tiny level? Well, it's not some kind of vague pull. It's a constant physical exchange of these boson particles. This snowball analogy is just perfect. Imagine two ice skaters throwing a heavy snowball back and forth. The very act of catching and throwing pushes them apart. That's pretty much how fundamental forces are created.
But for decades, this beautiful standard model had a huge, gaping hole in it. A key clue was missing, and it had all the detectives totally stumped. This was the central question, the big one, because without mass, all these particles would just zip around at the speed of light forever. Atoms could never form, stars could never ignite, and you and I could never exist. The universe would just be this thin, boring soup.
The solution, first dreamed up way back in 1964, pointed to a brand new suspect, an invisible energy field that fills all of space. We now call it the Brott-Englert-Higgs field. So think of it like this. A particle moving through this field is like a person trying to cross a crowded room. The more it bumps into people and interacts with the crowd, the slower and more difficult its journey is.
And this is the crucial point, so listen up. Mass isn't something a particle has, it's something that happens to it. It's just the amount of resistance a particle feels as it moves through this cosmic field. So to prove the field was real, the detectives needed to find its particle, the Higgs boson.
Now, finding a particle this sneaky, it required building the most powerful and sophisticated crime lab on the entire planet, and that is the Large Hadron Collider, or LHC, at the CERN laboratory in Europe.
Okay, just try to picture this. A 27-kilometer racetrack buried 100 meters underground. That's the LHC. Inside this massive ring, tiny protons are accelerated to 99.9999991% the speed of light before they're smashed into each other in these spectacular collisions.
And to steer those beams of particles, you need thousands of incredibly powerful magnets. To get them to work, they have to be kept at minus 271.3 degrees Celsius. That is colder than deep space. This lets them become superconducting, guiding the particles with just unbelievable precision. So when these particles collide, they create these showers of new, exotic particles. And the giant detectors surrounding the collision points take, get this, 40 million snapshots every single second to capture the evidence. That's like trying to photograph one specific unique spark from a firework millions and millions of times a second. It's just mind-boggling. And then, finally, on July 4th, 2012, after sifting through data from trillions of collisions, the evidence was undeniable. The scientists had actually managed to excite the Higgs field, they'd produced its telltale particle, and they confirmed a theory of mass. The case of the missing boson was officially cracked.
So, the mystery was solved. Amazing, right? But this incredible detective story leads us to an even bigger question. the one Pauline Gagnon asks in her book, Beyond Just Understanding the Universe, why does any of this really matter to us?
Well, it turns out the technology that has to be invented for this kind of basic, fundamental research has had these profound spin-offs. In fact, you're using one of them right now. The World Wide Web was literally invented at CERN just so scientists could have a better way to share the mountains of data they were collecting. This pursuit of pure, fundamental knowledge consistently pushes technology in ways that benefit all of humanity, and often in ways nobody could have ever predicted. It is a true engine for innovation.
And you'd think this engine of discovery must cost a fortune, right? But the cost is surprisingly small. The entire annual budget for all of CERN's research costs each European citizen about the same as a single cup of coffee. That's an incredible value when you think about its impact on science, technology, and really all of society.
You see, discovering the Higgs wasn't the end of the story, not by a long shot. It was the final brilliant confirmation of our best theory for that 5% of the universe we understand. But what about the other 95%? The biggest cases of all time, like the true nature of dark matter and dark energy, they are still wide open, just waiting for the next generation of cosmic detectives to solve them.